In this section, we will discuss the exposure process for photolithography in more detail. First, let's talk about what type of light is used to expose photoresist. A commonly used light source is a mercury arc lamp. These types of lamps have intensity maxima at 365, 405, and 436 nanometers, and many photoresists are designed to be sensitive to these wavelengths. The visible light spectrum extends down to 380 nanometers, meaning there is some overlap with the wavelengths of the mercury lamp. In order to ensure that the photoresist does not get exposed by the ambient light, photolithography labs filter the light, so only wavelengths above 450 nanometers are present. The filters make the light appear yellow, so you'll know you are in the lithography bay if it is illuminated with yellow light. Deep UV light sources are also common, including krypton fluoride lasers at 248 nanometers and argon fluoride lasers at 193 nanometers. Much more rare is new technology using extreme UV sources at 13.5 nanometers. If you do leave near UV-sensitive photoresist out in white light, it can be exposed. The effects of white light are visible after just 10 minutes, and after 45 minutes, the photoresist is completely exposed. So be sure to keep your samples in the yellow light areas of the lab or in an opaque box. Exposure tools fall into three general categories: mask aligners, steppers, and direct writers. Mask aligners print a mask design directly onto the wafer. Steppers shrink the mask design and print it in a repeating pattern across the wafer, and direct writers do not use a mask at all and directly print the design into the photoresist. On a stepper, each individual area that is printed in a single shot is called a die. Direct writers can use lasers or electron beams to print the design into the photoresist. So let's talk about some of the details of these different types of exposure tools. Each type has different resolution limits. At the NanoLab, the smallest features you can print are 1 micron features on a mask aligner, 0.6 micron features on a direct writer, and 0.25 micron features on a stepper. These minimum feature sizes are only possible if you work to perfect your process. They are not easily achieved. If you do need very small features, you may need to work on an electron beam writer, which can resolve 0.01 micron features. There are multiple modes available on a mask aligner, and each mode has its pros and cons. In proximity mode, your mask never comes into contact with your sample, but your minimum feature size can only be about 4 microns. Proximity mode may be useful if you need to keep your mask clean or if you have sensitive features on your sample that you do not want to be compressed by the mask. In contact mode, the mask comes into contact with your sample and the minimum resolvable feature is about 2 microns. In vacuum mode, the sample is put into contact with the mask and a chamber formed between the mask and wafer chuck is placed under vacuum to decrease separation further. In this mode, the minimum resolvable feature is about 1 micron. Once you have selected an exposure tool for your process, you can begin testing exposure conditions. Many factors, such as light intensity, feature density, resist thickness, and substrate material, will affect the required dose for your sample. There is no one perfect dose for all samples, so when you first begin your process, you must perform dose tests. During dose testing, you want to find a dose range that will work for your sample. There are certain things to look for that will tell you if your sample is underexposed, good, or overexposed. An underexposed sample will have areas that have not fully cleared, and the design dimensions will be smaller than desired. An overexposed sample will appear blown out, the design dimensions will be larger than desired, and the corners will be rounded. A correct exposure has sharp lines, the right design dimensions, and fully cleared open areas. Dose testing is done differently for mask aligners and steppers and direct write tools. On a mask aligner, you need to expose a sample at each exposure condition. On a stepper or a direct writer, you can program the tool to adjust the dose or focus for each die that is printed on the sample. Running an exposure job that tests exposure and focus conditions together is called a focus exposure matrix, or FEM for short. Keep in mind as you begin your process that you may need more test samples if you use a mask aligner than if you use a stepper or a direct writer. Here we have some images to help explain a few lithography-related definitions. As mentioned before, individual printed areas on a sample are called dies. These die often mark device boundaries and are arrayed across the wafer with space in between for dicing. The glass plate used in mask aligners and steppers is called a mask or reticle, depending on the tool it will be used on. If the pattern will be transferred to the wafer in a single exposure, the plate is called a mask. If the pattern is transferred in a series of stepped and repeated exposures, the plate is called a reticle. Boiled down, this means a mask is used on a mask aligner and a reticle is used on a stepper. On a stepper, the entire reticle does not need to be exposed all at once. An image, like the ones shown in the bottom left graphic, is an area on the reticle that will be exposed at one time and repeated across the sample. For example, image B may be exposed on its own across the wafer, and images A, C, and D can be exposed at another time. A mask or reticle is considered a dark field if most of the pattern is opaque with some clear areas. A mask or reticle is considered clear field if most of the pattern is transparent with some opaque areas. This is the end of video 3. In the next video, we will explain exposure and layer alignment and discuss a variety of process considerations.